Hello. This is Nicholas filming the second video on this lovely Tuesday morning, proving today that the Fibonacci sequence, in other words, the sequence where you start with a 1 and a 1 and then the next number is the sum of the two previous numbers. This Fibonacci sequence is a strongly divisible sequence. And so what does that mean? It means that it's a sequence that has the property that the GCD of two arbitrary Fibonacci numbers, say f sub m and f sub n, is equal to f sub the GCD of m and n. In other words, taking the GCD of two arbitrary Fibonacci numbers is the same thing as taking the Fibonacci number indexed at the greatest common divisor of the original two indices. Now, what I'm going to do here is I'm in this proof here. There's going to be a lot of lemmas. It's going to be more than a dilemma that's going on. So, first place I'm going to start is I'm going to assume that m is less than n, and so therefore by the division algorithm I'm going to let n be equal to km plus r, where r is less than m, but greater than or equal to 0. So in other words, r is the remainder, n goes into m k times plus a remainder of r. So now I get that the GCD of f sub m comma f sub km plus r, right? And now what I need to do is I need to establish a couple identities right here. And actually they're going to seem really odd. I'm going to actually use some matrices in linear algebra here. So the first lemma that I have is if I let A be equal to the matrix 0, 1, 1, 1, and I actually do have a video about this, about deriving Benet's formula for the nth Fibonacci number using this matrix and using eigenvalues. So this is actually a really powerful matrix in terms of Fibonacci numbers, because it is true that, and this is what I'm going to prove, I'm going to prove that a to the nth power of that matrix, is the matrix where we have f sub n minus 1, f sub n, and f sub n, and f sub n plus 1. Those being Fibonacci numbers, the nth minus 1 Fibonacci, the number, the nth Fibonacci number, and the n plus 1th Fibonacci number. And this is extremely easy to prove by induction. Obviously, for the first case, namely a to the 1, right, the sequence is f sub 0 equals 0, f sub 1 equals 1, f sub 2 equals 1, f sub 3 equals 2, and so on. And so, yes, n equals 1 is true. In other words, 0 is f sub 0, 1 is f sub 1, 1 is f sub 1, and 1 is also f sub 2. Now, we're going to assume then that a to the n minus 1 is the matrix f sub n minus 2, f sub n minus 1, f sub n minus 1, and f sub n. And then we're going to prove that a to the n is f sub n minus 1, f sub n, and f sub n plus 1. And now this is really obvious to prove, because a to the n is just a to the n minus 1 times a, which is just f sub n minus 2, f sub n minus 1, f sub n minus 1, f sub n times 0, 1, 1, 1. And when you do this matrix multiplication, you get, I'll do a little bit of it here. First we do row 1 and we dot it with column 1. So that's f sub n minus 2 times 0 plus 1 times f sub n minus 1. So we get f sub n minus 1. I do row 1 and I dot it with column 2. I get f sub n minus 2 times 1 plus f sub n minus 1 times 1. And f sub n minus 2 plus f sub n minus 1 is f sub n, which is the same thing as what we get down here. And then lastly, we're going to get an f sub n plus 1 here. And so this is true by induction. Now, the next thing I need to establish lemma number 2 is a formula, basically a formula for f sub m plus n. See, I have that already, except m plus n is km plus r. So I need a formula for that, and I'm going to derive it using that matrix that I just talked about. So what I'm going to do is I'm going to note the fact that since matrix multiplication is associative, what I can say is that a to the m plus n is equal to a to the m plus, or times a to the n, right, for that matrix. So in other words, f sub m plus n minus 1, f sub m plus n, f sub m plus n, and f sub m plus n plus 1 is equal to f sub m minus 1, f sub m, and f sub m plus 1 times the matrix f sub n minus 1, f sub n, and f sub n plus 1. And when I do this matrix multiplication, I actually am going to stop at the second part, so because I only need that part right there. What I'm going to do is, so first all I need to do essentially is just do half of it. So if I do the first part, I do row 1 and I dot it with column 1, I get f sub m minus 1, f sub n minus 1, plus f sub m, f sub n. And now when I do row 1 and I dot it with column 2, I get f sub m minus 1, f sub n, that n looked like a m, f sub n. So I do f sub m minus 1 times f sub n plus f sub m times f sub n plus 1, so plus f sub m, f sub n plus 1. And now I don't even need to find these other two, and I actually didn't even need to find this, because all I need to know is that if two matrices are equal, then every corresponding entry of the two matrices are equal, and that's just the basic notion of matrix equality. So what that tells us is that this entry right here is equal to this entry right here, and so I get that now f sub m plus n is equal to f sub m minus 1, f sub n, plus f sub m, f sub n plus 1. And now if I go back up top, what I had before was the GCD of f sub m, f sub km plus r, which is equal to now the GCD of f sub m. Okay, now we have f sub km minus 1. I'm using this formula here on this. So f sub km minus 1 times f sub r plus f sub km, f sub r plus 1. Now what I'm going to note is that, and this is going to be lemma number 3, lemma number 3 is that the GCD of m comma n is equal to the GCD of m comma n plus or minus km. In other words, what that says, and I'm not even going to go through a proof of this, it just says that if we have two numbers m and n, and we want to find their greatest common divisor, we can add multiples of one number to the other number as many times as we want, and that's not going to change anything about the greatest common divisor that they share, right? Because I'm just adding multiples of m to n, but I'm not adding any new divisors to it because I'm going by units of m. And so this I will consider proved. Now, what that tells us is that we need another lemma. We need to show that now, and this is going to be lemma number 4, I think the final lemma. Lemma number 4 is going to be that to show that f sub, it's going to be to show that f sub m divides f sub mn. And if I can show that, then basically the whole point of why I'm doing these two lemmas here is because if I can show that, then I can get rid of this second term right here, because it will just be a multiple of my original f sub m, and by this original lemma number 3, I can just get rid of it, right? I can get rid of this plus or minus km and just have that part right there. So now how am I going to show that f sub m divides f sub mn? Well, I'm going to go back, and in this formula right here, I'm essentially going to induct on n. And so what I'm going to do then is I'm going to let n go to n minus m in this formula right here, and you'll see why in a second. If n goes to n minus m, then I have f sub, if you look right here, I have f sub m plus n minus m, which is just n. And now I've solved for f sub n, which is what I want if I'm going to induct on n. So f sub n is equal to f sub m minus 1, f sub n minus m, plus f sub m, f sub n plus 1, so n minus m plus 1. So I've replaced every n with an n minus m. Okay, now what I'm going to do is I'm going to show the base case. N equals 1 is obvious in my opinion. N equals 1. Obviously, f sub m divides f sub m times 1, and so that's true. Now, I'm going to assume, I'm basically going to show that now that k implies k plus 1 for all k, and so therefore it implies n, because n is going to be equal to k at some particular point. So I'm going to assume that f sub m divides f sub mk, and I'm going to show that implies f sub m divides f sub m times k plus 1. Now, when I get that, let's see here. If f sub m, what I'm going to do now is I'm going to let, in this formula right here, instead of f sub n, which is what I want, or which is what I have, instead I'm talking about f sub m times k plus 1, and so that suggests to let n be equal to m times k plus 1. Now, what I can do is say that this is equal to f sub m times k plus 1. It's equal to f sub m minus 1 times f sub. Now, right here, I would have m times k plus 1 minus m, right up here. But m times k plus 1 minus m is just going to be equal to mk, because the m's will cancel out. Yeah, so just f sub mk plus f sub m, f sub, and now m times k plus 1 minus m plus 1 is going to be f sub k m plus 1. But now notice by the inductive hypothesis that if f sub m divides f sub mk, then we get f sub m minus 1, and I can replace this f sub mk, this is the whole point here, with some constant q times f sub m plus f sub m times f sub k m plus 1. And now that tells me that f sub m times k plus 1 is just equal to some constant, say q prime times f sub m, right? Because this part has a factor of f sub m and this part has a factor of f sub m. And so therefore, f sub m times k plus 1 is divisible by f sub m. And so therefore, we have shown that f sub m divides f sub mn by induction, right? We've shown this right here. So now, originally, we had the GC, and I'll write it down here real quick. We had the GCD of f sub m, comma, f sub km minus 1 f sub r plus f sub km f sub r plus 1. Okay, now I just copied that down from up here, from right up here. Now that tells me that since f sub m divides f sub km, this whole part here can go away by this fact right here. And so now I get that that's equal to the GCD of f sub m, comma, f sub km minus 1, f sub r. And now we've simplified things greatly here. So now if f sub m divides f sub mn, basically I'm going to want to reduce this even further so that I can get rid of this yucky factor of f sub km minus 1. And so notice now if instead I want to go from mn to km minus 1, what should I do? Well, I should probably let n be equal to k minus 1 over m. Because when I do that, m times n is m times k minus 1 over m, which is mk minus 1, or km minus 1, same thing. So now that tells me that f sub m divides f sub km minus 1. And so since multiplication is just repeated addition, this is just going to get rid of this factor right here because it's f sub r added to itself f sub km minus 1 times. And so now I just get the GCD of f sub m, f sub r. So this is an important point to note now because I've reduced the GCD, my original question, I reduced the GCD of f sub n, comma f sub m to the GCD of f sub m, f sub r. So essentially I've got the indices lower and lower and lower right here. And right, we know that because in the original proof we said n is going to be greater than m, and then we also said that r is going to be less than m, and it's going to be greater than or equal to 0. And so that tells us now that since these indices are just finite numbers, by the Euclidean algorithm, which is the whole point of why I did a video on this before, by the Euclidean algorithm, right, if I just ignore the f part, if I just ignore the Fibonacci part, and I just consider what I'm doing to the subscripts right here, what I'm doing is the Euclidean algorithm. In other words, eventually at some point, I'm going to get to the point where I have the GCD, if I'm looking just at the subscripts, where I have the GCD of m comma n is equal to the GCD of here m comma r is equal to, and I can apply this process as many times as I would like, but since they're finite numbers, eventually I'm going to get to the point where one of them is going to be 0, and one of them is going to be the smallest positive remainder, right, from the Euclidean algorithm. Call that remainder s, right? And the GCD of s and 0 is just s, right? So eventually, after applying this finitely many times by the well-ordering principle, the sequence of subscripts, of remainders, is going to truncate and end. And I'm going to call that ending point at s. So s is the GCD of m comma n. So now if I just add the Fibonacci part back in other words, the f part here, I'm going to get that the GCD, so that the GCD of f sub m, f sub n is going to be equal to, after, well, let me write it for, we show that that's equal to the GCD of f sub m, f sub r, which is going to be equal to, after so many times, the GCD of, and then the subscripts are going to eventually reach, one's going to be 0, one's going to be the smallest positive remainder, so say f sub s, comma 0, which is f sub s, right? But what is s? S is the GCD of m comma n. So that's equal to the f sub the GCD of m comma n. And with that, we have shown that the GCD of f sub m comma f sub n is f sub the GCD of m comma n. And now that we have that result, my proof that there are infinitely many primes should make perfect sense. And I hope that you have found this video helpful. And with that, we're done.